Good afternoon, almost everybody. Now, the program leads us now to the second keynote of this year's conference, and we are honored to have here Professor Bruce Jacobs from the University of Maryland. And I asked him, how should I introduce him? But I was also doubting myself, because he is a good example of how one should do things top down. He started with mathematics. He did an excellent study at Harvard, got cum laude for his study, and then he said, yeah, okay, there's something more. These machines that do mathematics. I want to understand how these things are working. Then he started programming them first. He said, oh, but this is serious. Oh, there are a lot of problems in these computers. So we should improve them. But in order to improve them, we have to know more about them. And then he enrolled in the graduate program in the University in Michigan, now Harvard. Right? And he was lucky to meet some great people that know a lot about computers and learn more about it. And he found, oh, the memory, this is the biggest problem. Even like in the 90s, memory is still okay. People start already talking about the memory bottleneck and all the other issues that will be related. But Bruce knew that this is actually the essential part of the computer system that is very important to understand and improve. And as a result, right, so many years later, after 2 books or 2 editions of the book, this is better for you to define. Yeah, he is one of the few experts in our field that knows everything about memory. So you could also define him as a Mr. Memory or Mr. Memory. And as you will guess, his talk is going to be about memory systems, and here's how to push all the boundaries to get them deliver the high bandwidth, high capacity, and the lowest power possible. And just as a confirmation of what I'm trying to tell you, he was invited by Micron and the Hydra Memory Cube Consortium to help them a lot with improving many of the aspects of the Hydra Memory Cube, and this is a very promising technology. So I think that he's one of the few people in academia that have the insight about the real state of that technology. So, the last thing that I can say, and he always would like to keep the safest set of options. So he founded a company that is known as Coil Guitars, LLC. He is the CEO of that company, and they're kind of successful. They are making electric guitars that many artists are using. So if the memory system does not work, then it's always
literally dozens of people.
Excellent. So, Bruce, please, go ahead.
Thank you, Georgi. It makes it sound like I know what I'm talking about. I knew what I was doing when I got here, I guess.
Hi, I'm Bruce. This is me, and today I'll talk to you about memory systems. And so one question that I get asked a whole lot is, you're a memory guy. Yes. What's coming up? What's the next memory system going to look like? What's the next memory technology? I get asked that a whole lot, and so I figured today would be a perfect opportunity to say, this is what's coming up. That's not something you can really publish. So this is actually kind of a perfect forum to get that discussion. So today's talk is going to be, here's what's coming up. Here's an outline of the talk, State of the Union, what we've got today, what some of our solutions and problems are. Recent developments, these are things that they've been announced, or they've been designed, or they've been just released, but they haven't hit really mainstream yet. But they're definitely coming. And then future developments, this is more of a prediction, but even though I don't normally try to make predictions, I feel relatively safe about these. I think these are going to hit your desktop at some point. It's not a question of whether, it's just really a question of when. So this is what you're going to get. And it's an hour-long talk. but because of the format here, I've shortened it. So we're going to skip all the boring stuff and go right into recent developments, more or less. So they said, yay, everyone. All you really want to know about is HMC, I guess. Oh, and by the way, the stuff that's in red and asterisk, those are things that we had a hand in. We either researched a lot, like buffer on board systems, or like HMC, as Georgi said, we had a hand in developing that. We did for those of you who don't know, we did the cycle accurate simulations for Micron while the HMC part was in development over the past, at this point, 6 years. So, so this is stuff that we've done, the stuff in red. State of the Union, real quick. This is what today's enterprise systems look like. This is the technology that everybody knows about. We have cache coherent CMPs. They've got integrated memory controllers in them. They're going to be driving 2, 3, 4, and at some point maybe more DRAM channels, which is crazy because each of those things is 240 pins, so you got 1,000 wires to connect to your DRAM system because you want so much bandwidth and because you want capacity, and we can't figure out how to get capacity in a single channel. That's kind of a fun problem. We're still using disks as the I/O backend, and then we use enterprise-grade NAND for a cache, basically. So this is the thing that we're basing the world off of. And I've condensed my background slide to this. Here are the unmet needs. These are the problems that we still have. These are the problems that we still want to solve. And yes, there is a capacity problem. Yes, we still have a bandwidth problem. And of course, there's a low power problem in the memory system, which is now consuming a healthy fraction of a node. 30–40% of a node is memory. That's where the power is going. Oh, and also, I can't really see it very well, but this is a Google data center. We would really like it if the memory took up less space, because if you can fit it in a half-size building, there's half of your cooling costs. In an enterprise class system, half of the electricity goes to cooling. You think that it's all going into the computing. It's cooling. So if you can make the building smaller, you just saved a lot of energy. And by the way, scaling's not a solution anymore, at least the way it was. Here's just some results from a recent PhD of mine, Ishwar Bhagi, who just graduated. So this is the effect of scaling on DRAM refresh. And the bottom line is, as you go to higher densities, you've got worse overheads in both performance and energy. Okay, so we've got execution time and latency over on this side. We've got energy on this side. So this is giving you the breakdowns of various components of energy. Scaling is making things worse for refresh. Refresh is now a significant fraction of the total energy and the overall execution time. And higher speeds of DRAMs are contributing to background power because you have this fast clock that's always on. So scaling is not a solution that it used to be, at least for the memory system, at least for DRAMs. So that's it for background. Now we're going to talk about some recent developments. So here's some stuff that's been announced, hasn't quite hit mainstream yet. We're all familiar with DDR3. Went from about 800 megabits per second per channel per pin, and it topped out around 2 gigabits per pin. DDR4 starts there and doubles it. That'll be coming out soon. It's already been announced. I think products exist. On 5.3, so this is the flash interface, for NAND flash interface, and it's going over the 8-bit channel. So this is really the digital component of the NAND interface. On 5.3 topped out at 500 megabytes per second. On 5.4 was just announced in like April or May of this year, and they're pushing it up to 800 megabytes per device. Now that's per device. That's per flash device. 800 megabytes per second. So you've got an 8-bit wide data channel on that thing going at 800 megabits per second per pin. That's cool. People have been begging for flash bandwidth. The industry has responded. We should be thrilled. I mean, this is cool. This is basically, flash devices are going to be as fast as last generation DDR3 devices. And that's fast. That's really fast. We think of flash devices as these slow I/O components, and yet we're getting bandwidth. Yay! Packaging, so we're moving from this package on package model to a wide IO2 model, which is really cool. I mean, this right here is what the memory industry has been doing for years. They've been stacking chips to give you capacity within a single chip, but they've got these high inductance bond wires that go out to your pins or your solder bumps, and so the things that connect the chips limit your internal bandwidth. They limit the speed that you can drive that chip at. And it's not any better when you do package on package because you still have the same bond wires. Well, with wide IO2, it's all going to be, they've come up with the interfaces through which they're going to have internal through silicon vias. High bandwidth, really good. This is coming real soon. Now, so I said that the memory system has been using the chip stacking, and now they're moving towards through silicon vias. A really good example of that is Hydra memory cube from Micron. This is the thing that we did the cycle accurate simulations for. You've all seen this picture. This is basically the idea is you're going to stack a bunch of DRAMs on top of each other, and the reason they call it hybrid is because the bottom layer is a logic chip. So the reason we've been talking about, PIM and things like that for years and years, and the reason it never worked is because DRAM really wants to be fabricated in a DRAM-specific process, and logic wants to be fabricated in a specific process that's tailored for logic. And so it's really difficult to combine the two in one process. You either make an inefficient DRAM or you make inefficient logic. Well, these guys address that problem by stapling together things that are different technologies so that you can have logic at the bottom layer in a logic fabricated chip. So it's a really cool concept. Here's more pictures. These are all from Micron. These are all publicly available things. They're just showing you close-ups of what that DRAM stack looks like. And the logic controller underneath, that's where they put the actual controllers. I'll give you a breakdown in just a moment. Here's a side view of a 4-high stack. They're shipping 5 high stacks. 8 high stacks, twice this. But so this is one of their Gen 1 parts, giving you a 4-high stack of the through silicon via and the solder bumps that connects the chips.
The solder bump goes to the substrate is on the bottom of the memory. Vias go all the way through to the logic layer.
So the logic layer of the chip, or the logic layer of the substrate. Yes, exactly. The vias go all the way through every DRAM die and terminate at the logic die at the bottom. And
what's the dimension on those vias?
Don't know. I'm sure it's out there, but I don't know. So here's what the thing looks like, basically. Here's the way to think about how these things are built. You start with a DRAM die, okay, and there's nothing but DRAM on it. And actually, one of the cool things is that they can take some of the logic circuits that you normally have on the DRAM die. So I don't know how many of you are aware, but over the years, the amount of storage, I prefer fingers because I never lose it and I never push the wrong button. So I know, you probably think that I'm doing like, animals and figures and stuff, but I find it far easier to work that way, sorry. And I like a laptop that I can jam my finger on the button because then I know I'm not. Oh, well. Anyway, so I always hit the reverse, or and I wind up or exiting the slide show, or just the wrong thing happens. So this works. It works. Don't if it's not broken, don't fix it. All right. So as I was saying, one of the cool things is over the generations, the amount of die area on a DRAM die that's devoted just to storage cells is going down, as you can imagine. So, I mean, you've got to have some logic to get at those capacitors. You've got to have muxes and drivers and interface pads, and you've got to have stuff that isn't cells, right? But the problem is the proportion has been going down year over year, and DDR4 parts are something like 50%. 50% of the die area is cells, and 50% of the die area is just wires and muxes and control stuff. Stuff that really has nothing to do with storage, except you had to use it to get at the storage. Well, what they've done is they've pulled a lot of that, as much as they can, out of the DRAM, and they're going to shove it in the bottom layer, which is really cool. I mean, it doesn't matter to us. It just means that their costs are going to go down, and hopefully that means they're going to pass some of the cost savings on to the consumer. But, so, here's how it starts. You start with a DRAM die. You chunk it up into a bunch of partitions. And I believe the one that's shipping is either chunked up into 16 pieces or 32 pieces. I think 16. Actually, I have a picture of the die, so you'll see. You get another one, and you stack it on top. You make another one, you stack it on top. And then you stack a couple more. And you get a stack of about 8 high. Okay. Each of which is divided into partitions. At the bottom, you put a logic die, and the logic die is going to serve several purposes. One, you're going to put controllers down here that are going to talk to the DRAMs, and this is also going to talk off-chip to the rest of the world. Looks like this. They call this a vault. It's analogous to a DRAM channel. You have a controller down here who's only controlling the DRAM components that are directly above it. So this is like a DRAM channel with 8 ranks. These things are called partitions. Why they didn't call them ranks, I don't know. They're called partitions in Micron terminology. They correspond to DRAM ranks in a normal DRAM channel. And each of these is internally banked as well. Logic-based I/O control. Here's what the thing looks like. Okay, here's a die. I don't know if this is their shipping die or not. I believe so. I think this is a recent chip. But this is showing a chip with 1, 2, 3, 4 times 4, 16 partitions. Okay? So, they got 16 partitions. You can see that each one is banked internally to at least a degree of 4. So that would be a bank, that would be a bank, that would be a bank, that would be a bank. And you can see all the vias, all those little holes. So they're good. Yeah. It could be. Yeah, I don't know. I would imagine they're on the order of a pad. But okay, yeah, good point. Pads are about 60 microns. But, So, what does the logic die look like? It's going to be bigger. It's going to have to be bigger because it's got extra stuff that's got to talk to the rest of the world. You've got a vault controller that's going to talk to the partitions directly above it. You tile that thing out 16 times. They've got I/O ports, 4 of them. Each of them is full duplex. So they've got a high-speed channel out and a high-speed channel back. So each of those ports is full duplex, bidirectional, simultaneous, high-speed stuff. I'll give you the numbers. The numbers over here in just a second. So each of these things gives you 80 gigabytes per second. Each port, 80 gigabytes per second. 80, not 8. 80 gigabytes each port. Okay. And you've got a crossbar switch connecting everything to everything. It's not like a half crossbar, it's not a partition thing, it's a full crossbar. Every port can talk to every controller with equal latency. Okay? Now, if you've got conflicts, like 2 requests want to go to the same thing, well then that's different. But it's not like one of these partitions things where you say like, these ports can go to these controllers with latency something, but if those ports want to go to these controllers, it's latency plus something. It's not that, it's symmetric, which is cool, which is really good.
How wide is the port? Just a single bit?
No. I believe it's 16 lanes in each direction.
So this crossbar is, these ports on there are 16, so it's 4 times 16.
Yeah. But it could be 4 times 16 times 2.
Yeah.
So, here are the details. The off-chip, these guys are high-speed SerDes, and they're serving a generic protocol. This is one of the interesting things. This is how Micron kind of chose to future-proof themselves. Because if this generic protocol succeeds, this, when you look at this, I'm not going to show it here, but when you see this, it's just a networking protocol. You're just sending things that look like Ethernet messages, effectively. You're sending a packet that says, I want to read this address, or I want to write this data to that address. That's it. There's none of this device-specific stuff. Every memory protocol has device-specific stuff in it. Flash protocols, you've got to do erase stuff. You've got to program, erase, and read. You've got DRAMs, you've got to do refresh that doesn't exist in other technologies. Every different memory technology has its own specific protocol. And so that means it's got to have its own controller. Well, what these guys have done is they've put the specifics into the vault controller so that this can talk a generic protocol to the rest of the system. So that means that your CPU can just say, I want to read location something. It looks like what your software sends to the memory controller, frankly. It's generic. So that means that at a later point, they could put whatever technology inside this thing they want. They could put flash, they could put PCM, they could put whatever. And the same protocol will work. Yeah, well, basically, Micron, my understanding of it, and this is an imperfect understanding, the question was, there's a consortium that did this. My understanding was that Micron designed this concept and then spent a lot of years going around the world trying to sell people on it, and the biggest thing that they had to do was sell Intel, and I don't know how well they succeeded on that, but they also had to sell at least one major DRAM manufacturer on manufacturing it. So they got Samsung to sign up, because then it's not a single supplier product. Because, I mean, if you have a single supplier product, it's going to die. Nobody wants to buy from just one supplier, because what if they stop making it? Then you've got this product that depends on something that no longer exists. So if you've got two major manufacturers building this, then the likelihood of it disappearing it's less likely. So people are more interested in buying it.
So the packets are constant size or quantity?
I believe they're constant size depending on what's in them. So I/O ports are up to 80 gigabytes each. So that's 320 gigabytes per second off of this one part. And the next generation, they're already talking about a next generation design, and they're talking about going 160 gigabytes per second per port, which just blows my mind. Here's the thing that I like. All right, here's the total concurrency in this part, and this is part of what we did in the studies, was to show how much concurrency you have to have in order to sustain those sorts of bandwidths. Because one of the things that we found is like, wow, it's wonderful that you can have hundreds of gigabytes per second, but it's one of these things where you're sustaining, let's say, 200 gigabytes per second or something like that, and then you have this momentary hiccup where two requests want to go to the same resource. And so for a very brief moment, your bandwidth goes down to almost nothing because you have back-to-back requests where the second one has to stall for the first one to do an access, and a read, and then a pre-charge, and only then can you start your second access, pre-charge, and read. So you get this momentary blip in your access pattern where everything comes to an abrupt grinding halt. So you go from sustaining several hundred gigabytes per second to almost nothing, but then you go back up to this. It doesn't sound like much, but if that happens 3, 4, 5% of the time, that slows down your execution by a factor of 2 or more. So you have to have a lot of concurrency to support this amount of bandwidth. And they've got a lot. So they've got 16 of those channels, 16 controllers. So you've got a factor of 16 there. You've got an 8-high DRAM stack. You've got a factor of 8 there. And then each of those partitions is banked internally between 2 and 8, to a degree of between 2 and 8. So your total concurrency in the system, the total number of requests you can have in flight, the total number of different things you can access, thereby reducing the likelihood that 2 back-to-back requests go to the same thing. Total concurrency is 200 and something to over 1,000 in one device. 1 DRAM. I mean, these are mind-boggling numbers to me.
What's the capacity of this thing?
It's gigabytes. It's not like 32 gigabytes. It's like
point.
yes,
Because
exactly.
you're throwing stuff in it so quickly, you fill it in no time, right?
Yes, exactly. But you're getting bandwidth. So what do people want more? And what this gives, this solves the bandwidth problem. It doesn't even address the capacity problem. But we've got other solutions for that.
We'll get 8 gig devices next year.
But these data rates, you need hundreds of this.
So, but this is a single device. So what you have to do is just build a system the way that you're building it now out of lots of devices. Now these are numbers that were produced at the Intel Developer Forum for a number of years ago. I can't vouch for their accuracy, but you know, this is what they are claiming. They compared a whole bunch of different technologies in terms of basically their bandwidth, their watts rating, and their picojoules per bit, and showed that the early on generations are really good in terms of, that's gigabytes per second. Gigabytes per second. So this was the Gen 1 cube. So this was the first one they designed. I think the one that's shipping is Gen 3. So this thing topped out at 128 gigabytes per second and gives you the best picojoules per bit, so the best energy per bit, even if the watts are a bit higher than others, but that's because you're getting a lot more bandwidth. And it kind of makes sense because, well, I'll get to you in just a second. The way that we get bandwidth right now is to have a whole bunch of DRAMs in parallel, and we access them simultaneously, right? So you say to 8 or 16 DRAMs, you say, give me, you know, address X, and they all work in lockstep. So each of them pulls down an entire row. So you've got that row times 8 or 16. You've just activated, and activating a row is the most costly thing you can do in a DRAM. So you've just paid your activate power times a factor of 8 to get tens of thousands of bits, hundreds of which you're actually going to read. Okay? So what these guys have done is said, let's not do that. Let's only activate 128 bits, or activate maybe 256 bits. And that's why the minimum, the access granularity is 128 bits. So they can control how much gets activated. It's an interesting way of doing things. So, and this is why they're giving you so much bandwidth, so that you can say, oh, okay, well, I don't need to get bandwidth out of multiple parts. I can get bandwidth out of a single part. And I get capacity out of having multiple parts, but I only talk to one at a time. It's kind of like a revisitation of the Rambus concept, but, you know, better. Trevor, you were going to say?
You answered the question. But going back to your earlier slide, you said it doesn't scale. Things are not scaling.
Right.
And that's because...
Well, I was giving one example. I mean, the problem is that
they're not scaling because of the layout of the chip and the access.
Well, we're just running into a problem where everything was getting smaller and smaller and smaller, and so the parameters would get smaller. So Trevor's asking about why aren't things scaling? Earlier I said that the scaling is not a solution to the problem. In particular for DRAMs, and there's a problem with the refresh. The problem is that in most things, when you scale it, you get better results. It's smaller, it dissipates less power, it takes less time, or something like that. DRAMs, as they make them smaller, they don't make the capacitance smaller. No. Because and this is why the cells get taller and taller and more folds in the polysilicon, because they have to keep the capacitance the same. If they make the capacitance smaller, they can't actually read the cell. Okay, sorry. Move on. All right. Running out of time? Okay, because according to me, I've gone about 25 minutes.
So the point is, it's an artifact of the way they lay out DRAM cells. You don't have
no, it's because you can't make the DRAM cell any smaller because you won't be able to read it.
No, but it's the bit line capacitance. You can change that by changing the aspect ratio.
It's not just the bit line capacitor, it's the capacitor. It's the capacitor, it's the cell. The cell, you can't just make the cells.
Is charging that.
Refresh is charging the capacitor. The access, doing the DRAM activate is you're pre-charging the bit line. So there's two completely different charging going on. So I was talking about refresh. The refresh is the cost is the capacitors. All right, so what is the performance? Here's some really early performance numbers. Let's see. So here's a comparison between DDR3 buffer on board. This is another thing that we had done lots and lots of DRAMs, a lot of narrow fast channels, and versus HMC. And so what I've got here are graphs that show instantaneous bandwidth that's consumed by the part versus time, and implicitly is not access time, but execution time of the application. Because they all run for the same amount of instructions, and so where the line terminates tells you how long the thing took to execute. So this terminates here, which means that it ran about 3 times faster than that. Okay, so you got several pieces of information. You've got how much bandwidth the thing is actually able to pull out of the part. You've got total execution time. And yes, sir?
Okay, so the question was that you compared peak bandwidth numbers on the previous slide for DDR4 and for HMC. So my understanding, as you described, that the pre-charge is localized to 128 bytes instead of like reading a whole
128 bits. Yes.
128 bits instead of like a whole page of.
Active? No. I don't know about pre-charge.
Okay.
I do know that activate is localized to 128 bits. I don't know what they do for pre-charge.
Okay. So.
I'm sorry.
What am I saying?
Refresh.
Yeah.
The pre-charge and activate. I'm sorry. Pre-charge and activate. So accessing the cells so that you can read them or write them.
Yeah.
That is done at 128-bit granularity, maybe 256. I don't know off the top of my head.
Yeah.
Refresh, entirely different matter, and they haven't even told us what they do.
Okay, so, but for the peak bandwidth for DDR4, the memory controller also plays a part because it reorders stuff so that it can get, as much to read out of an open page, as much as it can. But it seems like in HMC that is not the case, or is it still the same case?
Well, so what you've got in HMC is you've got a memory controller at the other end that is doing your reordering for you.
Oh, okay.
So they're not dumb FIFO memory controllers. They're not first in, first out, like single buffer. They've got deep buffers and they do reordering. They're intelligent memory controllers. So you don't worry about that. The weird thing would be trying to do scheduling where you get like some weird resonance between the scheduling you do on chip and the scheduling it does locally, where you get some unanticipated weird behaviors.
Yeah.
That's something that I could see happening.
Yeah.
We haven't seen it in our simulations, but you can imagine it would happen. Whenever you get multiple levels of scheduling, weird stuff happens. So the idea is that compared to a DDR3 1600 system, this is going to be several times faster. This is execution time. This isn't like average latency or something like that. This is execution time. All right, so some more Rosenfeld limit. So this is an interesting result that came from a recent PhD of mine, Paul Rosenfeld. He just graduated and is working at Micron. He's the one who did the hybrid memory cube study, one of the guys who did the hybrid memory cube studies. And one of the early problems that he had was, or we had, and the whole group had, was figuring out how to drive the simulations such that you could get a reasonable amount of bandwidth out of the part. Okay, does that make sense? You have a part that says, I can give you 320 gigabytes per second. Send me requests. And the challenge is to actually send the requests so that you can get 300 gigabytes per second. That's the problem. So, we started off with 2 cores, and we ran it through the Mars. We ran Mars simulations, so it's very accurate. We ran applications on top of Linux, on top of Mars. So very, very realistic. With 2 cores running Stream. Now, Stream is something that, in theory, is supposed to blow through the memory system. It's supposed to get the most amount of bandwidth you could possibly get, right? That's why they developed it. They called it Stream, because you're streaming through the memory system. 2 cores gets you like 30 gigabytes per second. 4 cores, 40, and 8 cores, the same. So Paul said, I wonder if it's the coherence protocol. Let's try a different coherence protocol. So we tried Mosey. Okay, so you get a little bit better for 2 cores, a little significantly better for 4 cores. You're actually up over 50 gigabytes per second. Tops out around, I don't know, 80 or 90 gigabytes per second from Mosey. This is out of a chip that's supposed to give you 320 gigabytes per second. So Paul said, okay, what if we just get rid of the coherence protocol? Just, now let's pretend that it works. Because, once you get rid of it, then it's actually not going to work anymore. But you can drive the simulator and generate a lot of requests. So ideal is, what if we had perfect coherence? So 2 cores, 4 cores, 8 cores, you still only get up to about 100 gigabytes per second, a little 120 maybe. So I said, all right, what's going on here? And he noticed that every request, you'd have a cache miss, cache hit, 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 and then cache miss, and then hit, 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 hit. So he rewrote Stream to use something that was strided to the degree of the cache line. Only then could he actually get 320 gigabytes per second. But, so that's on this thing. So, once you start missing the cache on purpose, 2 cores will actually pull 200 gigabytes per second out of the DRAM part. 4 cores basically is DRAM limited at that point. 4 cores will generate more than 320 gigabytes per second worth of requests, and 8 basically is equivalent to 4, because at this point you're limited by the DRAM. You're no longer limited by the CPU. But look at what's going on with Mezzi and Mosey. These guys didn't improve at all from the previous graph. Okay, so the bottom line is that coherence is killing us. Coherence is preventing us from making memory requests. Okay, yes sir?
So my experience with this is that many times you can also run out of resources such as MSHRs while trying to put out too many requests. So if you're limited by MSHRs, for example, if you have a
well, but these are all run on the same. These are all run on the same hardware simulator. So that's not MSHRs. It's the coherence protocol. Okay. So there were a couple of talks yesterday on coherence within CMPs and transactions within CMPs. Yeah, this is the problem. This is the problem to solve. And frankly, I don't know what to do about it. Well, actually, I have ideas. All right, so the last slide of recent developments, and it's just basically an observation that we've got a lot of recent developments that target bandwidth, and yet here are all the benchmarks that Paul looked at, multi-core applications that should be requiring a whole lot of memory bandwidth, and this is using the perfect, no coherence. So this is like the maximum amount of bandwidth that these guys should be able to pull out of the memory system, and none of them are very high. So people are saying, I need more bandwidth, I need more bandwidth. They probably need something other than bandwidth. All right, so back to the coherence thing. And this is just my one slide that's sort of borderline memory systems, because this is, kind of what we're talking about and what was talked about yesterday as well. What should we do about coherence? And I think what you're going to see is a lot of non-coherent chips. Now maybe you're going to have this bifurcation type thing where high performance and general purpose computing are going to have 2 different chips. Maybe not. but what should we do about coherence if what we're seeing is true? I mean, if it's really limiting performance to that degree, it's a problem that needs to be solved. And one of the observations that we had was, you know, this movement of data from one core to another core through its cache hierarchy, that's something that's exposed in supercomputers, you know, at like MPI and so forth. That's exposed. These guys are all using data flow and things like that to explicitly move data from one thing to another. Maybe this is the way we need to be writing code for these massively multi-core chips. Because, I mean, we're seeing problems at 2, 4, and 8. Imagine the problems you're going to have if you try to put 1,000 cores on a chip. It's, you know, it's not going to get easier. So I think there's going to be a trickle-down effect, like there has been in the past, from what they do at the really ultra-high performance. It ultimately winds up at the, you know, consumer-grade electronics. I think you're going to see the same thing. Yes, sir.
Yeah, I think the main problem what you're talking about is essentially the whole caching system was built towards like slow memory. So the thing is, of course, you have like L3 caches that are like gazillions of megabytes nowadays. And of course, that reason why L3, for example, is in the system is going away, or even L2, for example. So far, I think the coherence problem is not really a coherence problem per se, but the balance between the cache size versus the data class that you have in memory.
Okay, so yeah, we need to rethink this whole thing.
Yeah,
basically.
I agree with that. Yeah.
I agree with you. I couldn't agree more. All right, so here's some more future developments. Now, this is something that has been okay. So I'll be done in about 15 minutes. So tell them not to ask questions. No. All right, so I figure if you're asking questions, that means you care. And if 45 minutes comes up and you don't leave, just get out and go, and I'll shut up. That'll be like a signal. We don't find this interesting. Okay, I do the same thing in my classes. All right, so chaining. So this is something that's been announced, but they haven't really talked about it much because they're still kind of working on the packet forwarding heuristics, and that's some of the stuff that Paul did as well. But the idea is this: you've got 4 memory ports coming out of this one memory part, right? You got 4 ports, but there's no rule that says they all have to go to the same place. Okay, so you could have them all tied to the same CPU if what you want is lots and lots of bandwidth. Or you could do this. They've been talking about this is how they see building a typical, like a desktop or laptop style memory system, where you chain these guys together and create a linear chain, and perhaps this is outgoing and coming back or whatever, but they're saying that this is how you should be building capacity in your system, by chaining together the agency parts. Okay, and we've already seen examples of FPGA designs that do this. And you can also imagine interesting designs. Because what Micron has said is that this fabric will be coherent. So basically, you give it memory address and stuff to store there, and it will find where it's supposed to go. So if you give this guy data that's supposed to be stored there, it'll just figure it out. That's cool. That means that you can design some really interesting systems. There's a lot of design space to explore here that nobody's really looked at. So like all the grad students should be going, oh, yeah. So this is, I mean, there's a lot of untapped potential here. All right, so here's some more future developments. This is something that we're working on, non-volatile blank memory. And here's a little bit of background. So let's just compare SRAM, DRAM, and say NAND flash, for example. In terms of a couple things that we care about. What does it cost to buy, say, 10 gigabytes of this stuff? SRAM is well over $1,000. External SRAM. It's a lot of money to buy 10 gigabytes of SRAM. Which is why you don't have 10 gigabytes of SRAM in your laptop. To buy 10 gigabytes of DDR3 SDRAM, it's on the order of $100. It's like one stick, 16 gigabytes or something. It's about $100. Flash is about $1 a gigabyte. Enterprise grade is more expensive, consumer grade is less expensive, but it's somewhere around there. What is the size of that 10 gigabytes? Well, 10 gigabytes of external SRAM is basically a bucket full of chips. It's a lot of physical space for that. 1 DIMM of DRAM or 1 chip of flash. What does it cost to keep that storage alive? Well, SRAM is actually fairly cheap compared to DRAM because it's not refreshed. You just give it power and the feedback loop keeps it alive. It's about a watt to keep 10 gigabytes of DRAM alive, and that's mostly refresh. That's actually entirely refreshed because the power per gigabyte, that's the power to access it. And NAND, or any flash, any non-volatile memory, it's 0 to keep those bits alive. Once they're stored, they're stored. Now, scale that up to 10 terabytes, and you'll see that this 0 is really important. The difference between 0 and 1 is a big number. And this is the cost to access it. This is the interface. This is the cost to activate, read, transmit over the bus. So our observation is that, well, I'll just show it to you. Our observation is that years ago, SRAM was used as a main memory. Your main memory was SRAM. That was the way we built these things. DRAM didn't become used for main memory until they realized DRAM is really cheap. It's dense and it's cheap compared to SRAM. So we can build really big main memories. And so we started building main memories out of DRAM. And the disagreement or the objection was, but it's slow. And the reaction was, well, yes, it's slower than SRAM, but if you build an intelligent cache hierarchy in front of it, it shouldn't be a big deal. Well, guess what? DRAM is now our main memory technology. And it's no longer the densest technology, it's no longer the cheapest technology, and it's no longer the lowest power technology. It's time that DRAM goes the same way as SRAM and become a cache. Let's use something that's cheaper and denser and lower power for main memory. Instead of saying, okay, so I've got this main memory system and oh gee, I wish I had a terabyte of DRAM. Oh, why can't I get a terabyte of DRAM? Well, screw it. Don't even try to get a terabyte of DRAM because it'll cost you hundreds of watts just to keep those bits alive. Get a terabyte of flash. This is what your main memory system should look like, and in a few years it will. Okay? DRAM will be a cache. It will be a front end to some non-volatile technology. Now, is it going to be PCM? Is it going to be flash? Is it going to be NAND flash, NOR flash? Is it going to be NROM? I don't know. But it's not going to be DRAM. Because you can build terabyte systems now for the same, for nothing. I mean, effectively. We're doing it right now, we're just calling them SSDs. Wear out's a significant issue, but if you have enough things to strike your requests across, and if you do managed techniques, or if you use NROM or NOR, it'll last a long time. Probably. We still need to do accurate studies for that, and that's hard to do. So here's a tale of 3 memory systems. I'll give you some performance numbers that compare these two. Here's the way we do things today. All right, so we've got a CPU that's talking over DDR channel 2, a bunch of DDR backend. We've got some amount of last level SRAM cache. We talk over a PCIe channel to an SSD that's on the order of a terabyte. This is managed by the operating system. This goes through the file system, so it goes through a software stack. The main reason that it's slow. Otherwise, it would be relatively fast. At the other end, this is our ideal system. This is what we really, really, really want. You know, what we want is this, just bigger. We want to just take that DRAM system and make it huge. Okay? But if I have a terabyte of DRAM, it's going to cost me about 10 grand, and it's going to dissipate over 100 watts just in refresh power. Just in refresh power. Keeping those bits alive gets expensive once you have enough capacity. In the middle is this. This uses the same components as this, just configures them differently. The access to the flash, to the non-volatile memory, is not through the operating system, but it's hardware managed. This DRAM is a cache. It's just a cache. And we simulated it as a full-on cache, so the tags are stored in DRAM. It's not like you've got an SRAM tags and a DRAM data. No, no, no. We simulated it as, it's a cache, just like you think of cache. Instead of SRAM, DRAM. Okay, so this is going to cost the same thing as that, and it's just a little bit more expensive because getting in and out of this you're going to hit it more often. So it's going to be tens of watts instead of around 10 watts. Just because the access patterns are going to be more like address space requests and less like file system requests. And so here's the performance. Ideal is the red bar. That's the performance of the perfect system. If we had a terabyte of DRAM. And these are we intentionally chose applications that have really big footprints, like hundreds of gigabytes. So everything's normalized to ideal, which has a performance of 1. And so for each of these, we got 4 bars. We've got is the SSD-based system with single-level cells, and a hybrid with single-level cells, and then a hybrid SSD with multi-level. Because multi-level NAND and multi-level NOR, it just takes longer to access, because you're having to sense multiple values. So it's got a longer latency. So we wanted to see the effect of that. The first thing that should jump out at you is the fact that they're all within roughly the same order of magnitude. It's not like the SSD and the flash-based systems, the hybrid systems, are 100 times slower than DRAM systems. They're like, on average, they're about almost within a factor of 2 for some of these guys. It's a factor of 2. So factor of 3, factor of 4. You've just enabled a designer to make a main memory system of a terabyte or more, and all you're paying is a factor of 2 compared to an ideal, perfect DRAM system that you can't afford to build in the first place. That's a good trade-off. And this is kind of a funny result where that was when we realized not only that Mars comes out of the box with prefetching disabled, hardware prefetching disabled, we also realized that Linux, when Linux is running and realizes that it's talking to an SSD, its software prefetches the heck out of that SSD. It streams stuff out. Linux is really good. I've heard people say, oh, gee, we have this problem where the operating systems still think they're talking to rotating media, but they're talking to SSDs, and the performance is going to be bad. No, that's totally wrong. Linux knows when it's talking to an SSD, and it prefetches the heck out of that data, and it gets really good performance because it's getting better than ideal. It's because ideal didn't have prefetching. So, interesting result. All right, so some less easily quantified stuff if you go to this hybrid main memory. Well, first off, if it's made out of flash, it's journaled, and that's just built in. That's simply a byproduct of the fact that it's flash. You know how flash works. You can't overwrite bits in flash. If you want to rewrite something, you have to write it to a different physical location and then have a map to the new location, right? But that means that the old values are still there until you erase them. So if you exploit that and save the information, at least say for the previous version, now you've got a journaled main memory system, which is good. Anybody who has to do checkpoint and restore loves that concept. You don't need to have a virtual memory system. You don't have to have a TLB because your flash is already mapping itself. It has to. And if you've got something that connects all these non-volatile memory nodes, you can have something where it exports a global physical space. This is more for the supercomputer guys. They like having big, uniform memory spaces to program for. All right, so I'm done now. Recap. Today, we're really pushing all the envelopes. Tomorrow, bandwidth problems are going to be solved, but it may hurt the capacity problem if the hybrid memory cube chips are like a factor of 10 or 20 more expensive than normal DRAM. because you're just not going to buy a whole lot of it. Really soon now, I think you're going to have gigantic memories. You're going to have lower cost per bit, lower power, and I think there's a lot of potential for some really interesting software.
Thank you very much. You not only a bit on the coffee break time, but we also run over into the next session. Yes, you did that. I would say also, formal PhD advisors are not allowed to ask questions because they ask many questions during the presentation. Let's ask only one question, but it was the really important part. Dandy, please. Beautiful.
One question.
Yes.
Everything is fine, every large amount of bandwidth is made available, but the key is how are the memory controllers really programmed? It totally depends on.
You mean inside the hybrid memory cube?
Right.
They're high performance. They've got big queues and they do reordering, and they're intelligent memory controllers. They're not like dumb.
They should be part of the compilation process itself.
Well, but in modern CPUs, you don't. The memory controller isn't exposed to you right now.
I'm saying that it is better if it is exposed.
Okay. While I agree with you, I see that as being a big uphill battle with industry, because right now they're not. The interior of modern memory controllers is already a black box. They won't even tell you how they built it. The only way that we can figure stuff out is by reading Intel patents to get an idea of maybe what they actually put inside there. You know, and actually it's funny because some of their patents look like our publications from the 1990s. Thanks, Intel. So, but you know, and also Scott Rixner and other people as well. I mean, their stuff, what people have published in academia winds up being patented by others. But what they're doing for their specific heuristics, no idea. Absolutely no idea. But their structures all look like they're queued, they're reordering, they have multiple queues. One's queuing the requests, and then they've got another set of queues that queue up the DRAM specific requests. And then they schedule out of that. So they're very complex. They're very cool.
Okay,
but you can ask me as everyone's filing.
No. So let us take Bruce again. And